So my name is not Xinyi Chen. So she sends her regrets that she couldn't make it, and I am speaking in her place. It's nice to be, I think, giving my first talk at QIP in a decade. Yes, but I'm going to tell you about some joint work between me, Xinyi, Ashwin Nayak, Satyen Kale, and Elad Hazan. It's called Online Learning of Quantum States. Okay, and you can find our paper, which is, really like an omnibus, just sort of putting, as you'll see, we have a result with like 3 different ways to prove it, drawing on our different areas of expertise, and we decided to put them all together into one big paper. Okay, so my starting point, these are some spin 1/2 particles that, because of bad power pointing, have been sort of squared, okay. But my starting point is the fact, well known to all of us, that an n-qubit pure state requires 2 to the n parameters if you want to describe it, even approximately. This is one of the central facts about quantum mechanics, and what makes it strange is that we know that if you were to measure an n-qubit state, then you could only get out at most n bits of information. That's Halevo's theorem. Okay, so there seems to be this exponentiality that's somehow present, and yet that doesn't manifest itself. Where the somehow for operational purposes, the effective size of the quantum state is seems somehow a lot smaller than if you needed to explicitly describe the entire state on your computer. And so this is kind of what we want to understand, sort of our quantum states in different senses that will interest us, more like vectors of size 2 to the n, or are they more like, merely n bits, or polynomial in n number of bits? So, in particular, if this exponentiality is something that, we can't access, then that might sort of militate toward the view that that maybe, to a more epistemic view of quantum states, to use the fancy word for it. Okay, that, the amplitudes are just in our heads and are not really there in the world. Now, you could have the same discussion about classical probability theory, of course, where a distribution over n-bit strings also takes 2 to the n real numbers to specify. But in that case, it seems clear that the 2 to the n real numbers are sort of in our heads, are a mental construct, right? That they just represent our ignorance of the state, and what's really there in the state is just n bits. In the quantum case, of course, it's not so simple, because amplitudes, unlike probabilities, can interfere. Okay, but there's been a long line of works, and this has been one of, I guess, the main interests that I've had in my career, something I've come back to again and again, in trying to show that in many operational senses, an n-qubit state actually behaves a lot like a probability distribution over n-bit strings, that you can't actually get at the exponentiality. Of course, you can. We know that in certain senses you can. That's the whole promise of quantum computation. But in terms of how much information can we encode, or how many samples are needed to learn a state approximately, we would like to say that it's not exponentially bad, right? That we can that our n-qubit state actually is going to behave like n bits. That will actually be good. That will be something we want, because that will mean that quantum states are more manageable objects, things that we can actually handle. Okay, so let me make this more concrete with the example of quantum state tomography. Okay, so this is the famous task where you're given a bunch of copies of some unknown d-dimensional mixed state rho. Let's say you have a machine that spits out a new copy of rho every time you press a button, and your goal is just to learn rho as a d by d matrix. Okay, just learn the entries of the density matrix up to some precision. So you could say intuitively, it seems completely obvious that you're going to need about d squared copies of rho to do this. Why? Because it's a d by d matrix, and each copy of rho, for sort of Halevo reasons, is going to give you not that many bits, maybe log of d bits. And so if I want to recover, d squared bits, then I'm going to need about d squared copies. But do d squared copies actually suffice? Can you make that argument formal? Amazingly, this was really only worked out a couple years ago. Okay, in these beautiful works by O'Donnell and Wright, and independently by Zhengwan Ha et al. Okay, where they've established that indeed using the end result after tons of representation theory is that indeed the doofus intuition is true. D squared copies are necessary and sufficient for doing quantum state tomography. Okay, and this is a problem because remember that d is like 2 to the n being the number of qubits. Okay, and throughout this talk I'm going to switch back and forth between talking in terms of d and talking in terms of n. Okay, but if we need d squared copies of our state, that's like 4 to the n. Okay, and the experimenters have known this for a long time as a major practical problem with quantum state tomography. And until very recently, the record was that full tomography had been done on a state of 8 qubits by, I think, Rainer Blott's group. Very recently, the record was broken, and full tomography was done on a 10 qubit state. That corresponded to millions of different measurement settings. I don't know what that corresponds to in terms of grad student hours, okay, but these are it's clear that this doesn't scale. So a decade ago, I started wondering about, is there a better way? Well, it's clear that if there is a better way, you're going to have to change the question somehow. So that's what I did. So I proved a result back then that you could call the quantum Occam's razor theorem. That's William of Occam. That's a Gillette. And so what did this theorem say? Just to remind you, it said, let rho be some unknown d-dimensional quantum state. Suppose now that we don't need to do full tomography on the state. Okay, so we don't need to learn the full density matrix because we know that that's going to require too many samples to do. Right? There's just too much information there in the full specification of the state. Suppose instead that we've got some probability distribution over measurements. Okay, and for simplicity, I'll think of these as yes or no measurements. Okay, so 2 outcome POVMs for the aficionados. Okay, so the measurements come in one by one. They're all drawn from some probability measure, mu. You don't have to know what mu is. Okay, you just know that all the measurements are drawn independently from this mu. Okay, and then for each one, you are told the approximate expectation value of that measurement on the state. Okay, so you get to apply that measurement to a few copies of the state, and learn roughly what is the probability that it accepts. Okay, and now the question we ask is how much sample data of that kind do you need before you can start to predict the outcomes of future measurements that are drawn from the same distribution. Okay, so so it's like you get this study material, and then you get a final exam. Okay, the basic rule of any professor: don't put stuff on the final exam that wasn't covered in class. Right, so it all has to be drawn from the same distribution. Okay, to make things fair. And all you want is to just get right most of the future measurements. Guess the approximate expectation values for most future measurements. Okay, and you might do that with some state that is totally far from the true state rho in trace distance. It might even be the maximally mixed state. Okay, if that behaves like rho with respect to most measurements from your distribution. Okay, but you just want to get right most of the future measurements. And the amazing thing that turns out to happen there is that you can start predicting the outcomes of most future measurements after a number of sample measurements that is only logarithmic in D, the Hilbert space dimension. Or in other words, linear in the number of qubits. Okay, so you get an exponential reduction compared to the amount of sample data that would have been needed for traditional quantum state tomography. And a procedure that works for this is just the simplest thing that you could imagine, namely just take all of the sample data that you've got and then find any state, find any hypothesis state, right, that approximately matches all of that sample data. And then the theorem that one can prove says that with high probability, that state, whatever it is, will approximately agree with the true state on most future measurements that are drawn from mu. Okay? Yeah, and this is the surprising part. I already said that. All right. Okay, so how did I prove the quantum Occam's razor theorem? It was really just combining two facts, both of which were well known in their respective communities. Okay, the first one is sort of an upper bound on a certain type of dimension of quantum states considered as a hypothesis class. So there's this quantity called epsilon fat shattering dimension. Okay, and what you show is if I look at the class of all functions mapping measurements to acceptance probabilities, so all functions of the form f of e equals trace e rho, right, as I range over all d-dimensional mixed states rho. Okay, so each of these functions maps measurements to real numbers between 0 and 1, right, probabilities. I consider that class of real functions. As a class, it has this very low dimension in a certain sense. Its epsilon fat shattering dimension is at most log of d over epsilon squared. So what is this quantity? Fat shattering dimension. It's the largest k such that you can find k different inputs, x1 up to xk, in this case measurements, as well as real numbers, a1 up to ak, such that for all 2 to the k possible behaviors that you might want, like you could say, I want an f such that f of x1 is epsilon more than a1, and also f of x2 is epsilon less than a2, and so forth, right? For every combination of statements of that form, there is some function in your class that's consistent with all of them. So that's kind of a mouthful. But if you've ever heard of VC dimension, this is really just sort of the real valued analog of VC dimension. So it turns out to sort of be the right thing to look at if you're interested in learnability of real valued functions. And so that's the first fact, that quantum states considered as a hypothesis class have a small fat shattering dimension. And then you can once you know that, you can just plug in results that were well known in classical learning theory, and which say that any class of functions whatsoever that has small fat shattering dimension will also have an efficient learning algorithm. Okay, that the number of samples that you need to see before you can start predicting the function on future inputs, grows only linearly with the fat shattering dimension. Okay? So this reduces the entire problem to, well, how do you upper bound the fat shattering dimension of the class of quantum states? Okay, but that turned out to be sort of also already known from a different guise. Okay, namely, Ashwin Nayak had this lower bound for what are called quantum random access codes. Okay, so this was a beautiful early result in quantum information. It's sort of a generalization of Halevo's theorem. Okay, and what it said is that if you want to take n classical bits and encode them into a quantum state in such a way that any bit of your choice, just has to be any one bit of someone's choice, can then be read out later with high probability by measuring the state, well, then there's no way to do that with fewer than about n qubits. Okay, so for this task, even if you just want out a single one of the n bits later, right, you're still going to need n qubits to encode them. You know, quantum gives you essentially no advantage over classical for this problem. Okay, so that sounds like a real bummer. But basically, all I did is sort of turn that lemon into lemonade. And I just said, if you take, you know, Ashwin's lower bound and you think about it in a different way, it just is an upper bound on the fat shattering dimension of quantum states, considered as a hypothesis class. You may have to think about that a little bit, but it's, you know, fat shattering dimension, you know, is sort of literally is saying, like, how many independently toggleable degrees of freedom do we have in our, you know, set of quantum states? And it's saying it's only linear in the number of qubits. That's what Ashwin showed. Okay. Now, all of this ignored the question of how do you actually find a hypothesis state that's consistent with all your sample data. Okay, well, you know, that is, you know, now, for this we really are going to need exponential computation time, the number of qubits in general. You know, there's no real way around that, just for cryptographic reasons. Like, even for classical learning, you sometimes need exponential time, right? But at least it's no worse than that. Okay, so you can phrase the problem, like, find me a quantum state consistent with my sample data as a convex programming problem by just, like, minimizing a functional like the one there. Okay, and then you can solve that in time polynomial in D, in the Hilbert space dimension. So at least it's not, you know, exponential in D, right? Or, you know, doubly exponential in the number of qubits. And it's actually even better than that, because not only is it a convex program, but Elad Hazan heard about this a decade ago, and he was able to design a highly optimized, actually linear time gradient descent algorithm for this specific convex programming problem. Okay, so that was sort of the first inkling that we had that the techniques that you know, Elad knows were actually relevant for learning of quantum states. And then a student of mine actually implemented the algorithm, and yeah, the theorem appears to be true. Okay, but then a few years ago, I was talking with Elad, and he says, well, you know, pack learning is just ancient history. You know, none of us in learning theory care about it anymore. This, you know, distribution over inputs, you know, this whole probably approximately correct model, like, it's so retro, you know, we don't even, so he says, you know, what all the cool people are doing now is called online learning, okay? So I said, what's online learning? I think I'm wearing the same shirt there as I am now, but okay. I don't have that many shirts. Okay, so let me tell you what's online learning. Okay, and then, you know, that will raise the obvious question: can we do online learning for quantum states? So now we're going to suppose that our measurements, you know, our two outcome POVMs, E1, E2, and so forth, are chosen by an adaptive adversary. Okay, so they're picked by our worst enemy, someone who sees everything that we've been doing, and, you know, they don't have to draw them from any distribution, they don't need to satisfy any independence, no nothing. Okay, they just pick whatever sequence of measurements they want to try to screw with us. Okay, and now for each measurement, E sub t, you, the learner, are challenged to guess approximately the probability that it accepts some unknown state rho, you know, that you never directly see. Okay, so that's this trace E sub t rho. Okay, and you might be right, you might guess right, you might guess wrong. If you guess right, great. Okay, take a cookie. Okay, if you guess wrong, like if you're off from the truth by more than, let's say, epsilon over 3, then you're told the true value. Okay, or at least the true value, to within some error, which we could again say is epsilon over 3 or something. Now, your goal, should you choose to accept it, is to design a learning strategy where we have a bound on the total number of times that your guess will ever be more than epsilon away from the truth. Okay, now to be clear, you have no way of knowing in advance which rounds you're going to get wrong, right? Like the adversary, if it wanted, could just for the first billion iterations just choose some stupid measurement where you learn nothing about the state and then switch on the billion and first to some really hard measurement, unlike any that you saw before, right? Well, in that case, okay, you're going to get billion and iteration billion and one wrong. Right? So, your errors could be pushed arbitrarily far out into the future, but we want an upper bound on the total number of errors that are ever going to get made in the entire process before you eventually converge on the truth. Okay, so basically what happened was that Elad gave me this question. I thought about it, and I realized that there would be a certain generalization of Nyack's result, his lower bound for random access codes, that would imply a positive answer to this question, that online learning of quantum states, was also possible using only, like O of n mistakes, right? Number of mistakes linear in the number of qubits. So I told Ashwin about that. And then Ashwin was actually able to prove it. Okay, he proved that generalization, that bounds this quantity that's called sequential fat shattering dimension. Okay, and that gave us a proof. So then we're going to write it up. But then Elad said, no, I think we have like a more elegant way to do it using online convex optimization and very high-powered techniques, and maybe we'll even get better bounds. And then later he brought on his student Xinyi. Xinyi figured out the details of how that works, and then Satyen Kale joined later and was able to improve the bounds, bringing in more techniques. And meanwhile, while this was going on, I realized that there's yet a third way to prove the theorem, using post-selected learning, okay, which is a technique I've used for other things in the past. So we have two main theorems. Theorem 1 says there is an explicit strategy for online learning of n-qubit quantum states, like mixed states, which is going to output an answer that's wrong, away from the truth by more than epsilon, at most O of n over epsilon squared times. Okay? And it's not hard to show that that's tight, actually. Okay. That's actually the right bound. Now, Theorem 2 is what people in the business call a regret bound. Okay, so we can say, even suppose that the adversary is even more nefarious, okay, and gives you back answers that are not consistent with any actual quantum state, right? Well, you might still ask, can we do about as well as one could do? Right? And this is what's called a regret bound. Okay, so can we get like a total number of mistakes that's not much worse than what we would have done if we had just known from the beginning what was the best quantum state to use in response to all of these queries. Okay, and indeed we can prove a regret bound, saying that our total error, our total regret compared to if we had chosen the best quantum state after t iterations of this process is going to be at most O of square root of t times n being, again, the number of qubits. And the error can be either L1 or L2. Okay, the theorem works with both of them. And I should mention that this theorem can be shown to be tight for L1 loss, although we don't know if it's tight for L2 loss. Okay, so let me tell you my way to prove the theorem, because that's the one that I actually understand. Okay, so here's what you do. Okay, you start out knowing nothing about this state, right? So you say at the beginning, I'm going to make the stupidest possible guess. Well, what is that? The maximally mixed state. Okay, so then you just get, answer all the queries that come along, consistent with the maximally mixed state. Okay, you're probably not going to get away with that for long, right? This is going to cause you to output a wrong answer at some point. Okay, but as soon as that that happens, you just do the machine learning thing, right? You just okay, so now I'm going to have a new hypothesis. My new hypothesis is whatever you get by starting with my previous hypothesis, applying the measurement, conditioning on getting the right outcome, and then looking at the new post-measurement state, which we'll call sigma sub t. Okay. I'm told that the way to get a job in machine learning, right? If they ask you like what's 10 plus 6, you say 0. And then they say no, not even close, it's 16. So you say, okay, it's 16. And then they say like, okay, what's 3 plus 7? You say 16. So it's just, you do this thing, okay? So okay, now you do need a little bit more than that. You need to do amplification. So you have not just one copy of rho, but several copies in order to bound the sort of damage to the state. That in order to push down the error, and then we use this gentle measurement lemma, where if the error is small enough, then the damage to your state as a result of each iteration of this learning process can also be bounded. And that'll cause us to lose a log factor, but whatever. Okay, so let epsilon be a constant for simplicity. Then the crucial claim is that this iterative learning procedure must converge to rho, or more precisely to several copies of rho, after at most about n log n serious mistakes. Okay, and why is that? Well, let P sub t be the probability that the first t post-selection steps all succeed. Okay, then you can bound P sub t from either side. In one direction, we know that the maximally mixed state can always be decomposed as the true state, whatever it is, plus a bunch of other stuff. It's just a convex combination of those. And if we had started with the true state, well, then we would have gotten the right answers on all these queries, right? Because, we had taken care to ensure that the state is not damaged much by each iteration. Okay, but in the other direction, if we're post-selecting at all on getting the wrong answer, then that means that if we start with the maximally mixed state, then each time, even conditioned on getting the right answer on all the previous challenges, by definition, we're now getting the wrong answer with, let's say, a probability at least 1/3 or something on the next challenge, right? So that upper bound is decreasing exponentially with t, and now we just solve for t, and we find that the number of mistakes can be, just solving that inequality, can be at most O of n log n, so nearly linear in the number of qubits. Okay, so, this doesn't give an optimal bound, it doesn't give a regret bound, but, we've got other ways to do that, okay? So Ashwin's way of proving these results was to, as I mentioned earlier, to prove a generalization of his random access code bound from 99, which might be of independent interest. And it says that you can store, in an n-qubit quantum state, you can store at most a linear number of O of n classical bits, in such a way that any one bit can later be, of your choice, can later be retrieved with high probability by a measurement. And moreover, that is true even if your measurement basis, when you're trying to measure the ith bit, can depend on the first I-1 bits. Okay? So that's, think about that. So that's a stronger result. And that implies an upper bound, again, O of n over epsilon squared on what's called the online or sequential variant of epsilon fat shattering dimension. And once again, you can then use purely classical results from learning theory, in this case, a result of Rachlin et al. From a few years ago, that then automatically gives you an efficient learning algorithm, one that makes this number of mistakes, and also a regret bound of the form square root of t times n. Okay, now Elad and Xinyi and Satyen's way to solve the problem was just to hammer it with these hammers of online convex optimization, what's called the regularized follow the leader algorithm, which is like a gradient descent method using the von Neumann entropy of the state, and this matrix multiplicative weights method of Aurora and Kale. And this stuff, like, the problem of optimizing over quantum states kind of is a convex optimization problem, which turned out to be just an excellent fit to these tools that already existed. Actually, one of the main technical problems that they had was just that all the tools, for obvious reasons, are designed for real matrices, and they had to generalize them all to complex Hermitian matrices. So that did take some work, but this gave them optimal mistake bounds and regret bounds for L1 anyway. Okay, so there is an application of these results that I probably won't have time to tell you much about, but I've been interested in this task called shadow tomography, where you get just a small number of copies of a state, and your goal is to learn the state with respect to a list of known measurements, like E1 up to EM, with high probability by measuring only a few copies of the state. Okay, you can do this with d squared copies by just doing ordinary tomography, or you can do it with m copies by just applying your separate measurement to each set of copies. But what if you wanted to do it with a number of copies that was polynomial in only log m and log d? Is such a thing possible? So I raised this question a few years ago. I couldn't see how to do it, and couldn't rule it out. Eventually, I found an obstruction to ruling it out, which is that it is possible. Okay, and so I can do it using only this number of copies of the state. Again, d is the Hilbert space dimension, and m is the number of two outcome measurements on which you want to learn the state. Okay, and in retrospect, the proof is simply a matter of combining two different ingredients. One being the quantum Ore bound, which is something that I claimed to prove 12 years ago. My proof was wrong, but it was fixed, fortunately, a couple of years ago by Harrow, Montanaro, and Lin. And that lets you repeatedly search for a measurement where your current hypothesis state is far from the truth without much damaging your states. And secondly is the online learning theorem, which then upper bounds the number of updates that you ever have to make to a hypothesis before you converge on some state that must behave like the true state with respect to all of your measurements. Okay, I should mention, coming any day to an archive near you is a new paper by me and Guy Rothblum, which gives a brand new shadow tomography protocol based on a connection to an area of CS called differential privacy. And this is based on, ports over work from classical differential privacy in order to get a new shadow tomography protocol that uses this number of copies of rho. So we have a better dependence on M. Also, the new procedure is online, meaning the measurements just come in one at a time, and you just answer each one without having to see all the measurements in advance. And the new procedure is also gentle, which means you could apply it, and then your states at the very end are still not damaged much, and you can still reuse your copies of rho for something else. Okay, and this new shadow tomography procedure, is much more complicated to analyze, but once again, it explicitly uses the online learning theorem of this paper as a central ingredient. Okay, so there's some open problems. Can we generalize from 2 outcome to k outcome measurements? What is the optimal regret for L2 loss? What special cases of online learning of quantum states could we do with only a polynomial amount of computation? It's clear that we can't do that in general, unless we can break one-way functions and so forth, but we should be able to do that in some interesting special cases. And finally, what is the true sample complexity of shadow tomography? I'm not even sure that it has to have any dependence on the Hilbert space dimension D. And maybe it only depends on log M. All right, let me stop there. Thanks.
Okay. I think we have time for one question.
Mike is coming over.
So I got befuddled on the slide where the title was My Way. Can you flip back to that real quick? So where I got confused here is in the problem setup, it sounded like what you were being told if you guessed wrong was the probability, trace row E.
That's right.
But here,
Yep.
when you say post-selecting on getting the right outcome, it sounds like you're talking about actual quantum measurements that don't reveal that, but give a 0-1 outcome.
Yeah.
I'm confused.
Okay,
What's going on?
it's just because I'm hiding the details, okay? You actually apply your measurement, in parallel to a bunch of copies. Remember, I said that we're going to use amplification, so we have a bunch of copies, and then you post-select on approximately the right number of them, giving you the outcome that you want, okay?
Okay, let's think. Scott again?